Neuroplasticity, which is the ability of neural systems to reconfigure the strength of synaptic connections based on experience, is a hallmark of neuroscience. And even though it has been studied for a few decades now, many aspects, and especially mechanisms associated with synaptic change, remain poorly understood. It has been shown, for instance, that timing between two spikes emitted by two different neurons play a role in the outcome of synaptic plasticity. But it has also been shown previously that the rate of activity between two coupled neurons also modulates plasticity differently. So there is an interplay between timing and rate, for instance, components in synaptic change. In more recent years, calcium dynamics, so calcium transients, so the motion of calcium ions inside neurons, have been implicated in synaptic change. So understanding the dynamics of such calcium transients can lead to better mechanistic models of plasticity, or better descriptive mechanistic models of how plasticity change take place and what are the mechanisms important for it. In this work, I'm going to be talking about a calcium-based learning rule, more precisely a Hebbian learning rule, which means that it's a prescription of how the weight or how the synaptic strength between two neurons, so it's a local learning rule, takes place. And in this case, what we model inside the learning rule is the dynamics of the calcium transients, and they are what's dictating inside such a learning rule whether potentiation or depression is happening and when. So in order to exemplify such a learning rule, we're going to be talking about two networks topologies. So in the first one, we're going to be talking about a feed-forward network embedded with such learning rules. So the connections between the neurons inside such a network use this calcium-based learning rule. And then this network is put to the task of learning to recognize handwritten digits. And we can see then how the dynamics of such calcium traces inside such a learning rule enable the learning, the correct learning of the classes, of the digit classes in this case. So the network properly learns how to recognize digits. The second case, we're going to be looking into a recurrent neural network. So it's a network that is used in the scenario to model working memory. And what we're going to be looking into then is first, how such dynamics, such learning rule can enable the formation of memory-like representations inside such a network. And then we're going to be looking into what's important for such representations to be stable inside the network. And for that, we're going to be looking into some metrics coming from graph theory to understand what are the topological features inside such a network that are important for a stable memory representation.